Hi everyone. Today we are going to talk about two-sample t-test. Last week, as you remember, we talked about the one-sample t-test, and this week we are just going to learn how to sort of compare two groups to each other using this statistical test method. One-sample t-test and two-sample t-test are very similar. The only difference in a two-sample t-test is that instead of having one group, you have two groups, group A and group B, and then you test it either if these groups are equal, bigger or smaller than each other. Okay, so this is basically the case where you compare two groups with each other and find an answer based on that. Conceptually, it is very similar to one sample t-test. For example, if you were to test if two groups are similar or not, let's say your job was to see if these two groups are uh, not similar or different from each other, right? So that if I am testing if the groups are different from each other, right? So we remember that the null hypothesis was the opposite of what we were testing. In that case, my null hypothesis is going to become E is equal to B, okay? And my alternate hypothesis, if you can disprove the H0, is going to be that A is actually not equal to B. This is the two-tailed version, right? And if you want to do one-tailed, we will have to ask the question of, I'm just going to write it here, that the A is smaller, right, than B, or A is, sorry, A is bigger than B, or A is smaller than B. So if I'm testing A is bigger than B, right? In that case, my H0, right, is going to be the opposite of that. So that means that A is either smaller or equal to B, okay? And my H1 is going to be A is bigger than B, okay? So this is a one-tailed because we are only interested in one direction, right, in our sort of distribution. And if I was asking whether if A is smaller than B, right, my H0 is going to be A is larger or equal than B, and H1 is going to be A is smaller than B, and this is also one-tailed. Okay, and these are the only three combinations that you could have in this case. Okay, so what it means to do a two-tailed t-test then? Okay, so let's think about what this means. So let's say I have a population called XA bar. Okay, so that's basically measurements of measurements belonging to group A. So let's XA bar, here's the mean value. And let's say I have another set of measurements, right? That's the XB bar. That is the group of measurements belonging to group B, which has a mean around XB bar. So what I want to create to do a two-sample t-test is basically take these two into account and then make a combined sort of population, okay, that is centered around H0, okay, and H0 says, if we are doing a two-tailed test, it will say A is equal to B, okay, and then in that sense, within the 95 percentile, let's say we are doing 95 percentile, in this area, okay, the difference between XA bar and the XB bar is going to be 0, okay, and if it's in this region, XA bar minus x b bar is not equal to 0. Okay, so that's basically, we reduce the two populations into a difference in populations, and therefore we can do it almost the same procedure that we follow with the one sample t-test. The difference then is that the Sx bar, which is sort of the standard error of mean, right, is going to become S xa minus xb bar. Okay, so this is basically affected by both of the measurements, and then the this basically I'm just going to refer to it as SAB. Okay, is going to be just the RSS of the SA bar square plus SB bar square in square root. Okay, and our t-score is exactly the same. Okay, as we did before. The difference is we have a minus a bar. Let's do it x a bar because we were talking about that way. X a bar minus x b bar divided by s ab. Okay, and that's going to be in absolute values, and our t critical, right, is same as before. Okay, so basically the only thing that's changed is that the if you remember the one sample t-test, we said the x bar minus a hypothesized value divided by the sx bar, right? So the sx bar becomes the combined standard error, and then the hypothesized value are changed by the mean of the second group. So, but the whole procedure is exactly the same. So let's do an example. Okay, so the example says that there's a drug for increasing the athlete performance. Okay, and they have tested two groups of athletes. Okay, group A is basically no drug control. Okay, so these are athletes with no drug intervention, and then group B, okay, is the drug control, drug experimental group. Okay, so they are basically give this drug to group B, and they give a placebo drug to group A, and at the end of the experiment, right after the drug, they basically measure the blood oxygen levels as a measure of performance, so that the outcome here is performance, and the performance is measured by the blood oxygen levels. Okay, during running, right? Okay, so then let's say let's make up some data. Group A blood oxygen levels were 7, 3, 6, 5, 6, and 13, and Group B was say 12, 5, 11, 11, 9, and 18. Okay, we can readily calculate the sample statistics from here, so I'm just going to go ahead and do it here. A bar is going to be 6.66. Standard deviation is going to be 3.38. Standard error is going to be 0.56. Our sample size is 6, and degrees of freedom is 5. Okay, I can do the same thing for B. Mean is going to be 11. Standard deviation is going to be 4.24. Error is going to be 0.7. Sample size is going to be 6. And then the degrees of freedom is going to be 5. Okay, so with this said, we need to test the our hypothesis, and then hypothesis basically was saying that the group A and group B was combined, sort of compared, and then the hypothesis was that the drug increases athlete performance. Okay, so that's the question. So that means that we have an increased blood O2 levels, right? That also means that. So that means that our H0, right, automatically is going to say that no, there's no increase, right? So that means that the group B is going to be is either smaller or equal to group A. Okay, so that means that there's no effect of the drug. Okay, and then our alternate hypothesis then will say, okay, group B is going to be bigger than group A, which means increased performance. And inherently, we are going to test the null hypothesis, okay? In that case, if you have imagined, since we are only doing the if A is smaller than B or B is larger than A, that means that this is a one-tail test, t-test, okay? And that means that the let's say they want to know this at 99.9 percentile. Okay, so let's say this is not 95, but 99.9. This is pretty common, right, in clinical type of trials. For some sort of measurements, it's okay to do 95 percentile, but if there's a study in relation to human health or exercise, you usually want to raise the bar to 99.9 because it's health related and you want large number of samples as well. So this is just a sort of a demonstration. Okay, so then the in that case, our T number is going to be T. We know that the degrees of freedom and 99.9, right? And degrees of freedom in both cases are 5. So then in that case, it will be T 5, 99.9. We are going to the table at the end of the this lecture notes about two sample t-test or the lecture notes from last week. It's the same. We will find that our t value, right, is 5.87, and that's the t critical. Okay, so then we know that the SAB, right, which is sort of the combined standard error pooled variance, right, is going to be defined as SA square plus SB square in square root. Okay, it's going to get you 0.89 if you do that math, and then the t-score is A mean minus B mean divided by the SAB, make this a little bigger, AB, and that's basically 4.9. Okay, so then the answer to our question is that, okay, t-score is smaller than t critical. Okay, that means except H0 and drug has no effect. Okay, so that basically told us that the drug that we are using has no effect because we have determined that the our t-score, right, was smaller than t critical. And basically, based on this experimentation, we were not able to find the difference between group A and group B, which is okay. So then I wanted to tell you something about, so this is an unpaired t-test, right? So we have just done unpaired. That means that the two groups are not related. are not related, right? So that means that we had a group of athletes who take the drug, and we had a group of athletes who didn't take the drug, and then we have sort of compared it, and then we have found that. So there's also an experimental procedure that you can do called a paired sampling. That means that the the they are the same athletes, meaning that the samples, the group A, let's say this that way, group A and group B um, is the same. So what it means? So in that case, in unpaired test, we have made it so that the group A and group B are totally different athletes, right? We just recruited 6 athletes in one case and then 6 athletes in the other case, and then we had 12 athletes total. So the paired test would be this way. So you have 6 athletes, right? You basically run them, okay, and then get their blood oxygen levels, okay? And after a rest period, say like a couple of hours or something like that, you give them the drug and then you run them again, and then you see if there's an increase in their performance. But they are the same athletes, so that means that you are testing the same subjects before and after a treatment. In the unpaired, you test a group of athletes with treatment and group of athletes without treatment. And that gives us a little bit of more power in our experimentation, right? So let's do it this way. So the before drug, let's say our data didn't change. Before drug, right? The athlete performance was 7, 3, 6, 5, 6, and 13. Okay. And then after drug, okay, it became 12, 5, 11, 11, 9, and 18. Okay. And since they are the same athletes only before and after, I can basically define something called the difference, okay, between the two. Okay, so that basically difference is going to be here is that the 12 minus 7, it's going to be 5. 5 minus 3 is going to be 2. 11 minus 6 is going to be 5, and so on. So it will be 6, 3, and 5. Okay, and instead of using these two groups, now I'm just going to use the difference between them. And if I do that, you will see that the mean difference is going to be 4.33, okay? And then SD, okay, standard deviation is going to be 1.5, and my standard error is going to be 0.25. The H0, meaning that my null hypothesis is going to say that the difference is going to be 0, meaning that there's no change between before and after drug treatment. And H1 is going to say that the D is not equal to 0. Okay, so this basically becomes a one sample t-test in a sense that your t-score is going to become d bar divided by SD bar. Okay, and if you do that for this example, we'll find that this is 17.26. Okay, and that's my t-score. My t-critical didn't change, so my t-critical is still 5.87 from the previous example. And comparing these two, then I can easily say that the t-score is actually larger than t-critical, right? So then we can reject H0. Drug increases performance. Okay, so basically, what happened was that when we did the unpaired t-test, meaning that two groups are separate, um, versus the paired t-test, where the groups are the same, you're just treating before and after and measuring the outcome. we can say that this drug increased performance, right? Because it increases your statistical power in a sense that you're testing the same subjects. Um, and basically, these are the two different ways you can do a t-test, right? In two sample t-tests. Let's write them again. Two sample t-test. Okay, tests the difference between group A and group B. Okay, for more than two groups, you're gonna have to go ANOVA, so you're not doing anything like that. You can do a two-tailed t-test, whether if these groups are equal or not. So that's two-tailed. Okay, and then you can test whether A is smaller or larger than B. These are one-tailed tests. Okay. And you can also do unpaired or paired testing. Okay, so those are different options or different ways that you can do the two testing between two groups. And based on that, you can statistically say if these hypotheses were either accepted or rejected using this type of statistical test. Thank you.